This is part 2 of section 10.1, radicals and the Pythagorean Theorem. We just finished example 4. Now for examples 5 through 8. Example 5. Ella rides her bike each weekday 34 blocks west and 16 blocks south to get to the company where her mother works. About how many more blocks does she have to ride her bike than if she could simply travel from her school straight to her mother's place of work? Draw and label a diagram. Okay, to solve this problem, first of all, let's start with the beginning part. Ella starts right here. Let's say it's her home or something. Here's Ella. This is where she starts. And she's going to travel 34 blocks west, due west. So that on a map would be to the left. So we go left. I'm going to use a dashed line. 34 blocks. 34 blocks west. That's the direction there. And then from that point, she travels due south, 16 blocks, it says. When she starts to turn and move south, she creates a right angle as she moves southward. So this is a right angle. And let's say this represents 16 blocks south. 16 south. So she's at her destination, her mother's company, right there. And the problem's asking us, how much longer does she have to travel when she takes her bike going 34 blocks west and then 16 blocks south than she would if she could just go straight from where she starts to her mother's place of work or company in a straight line distance. And of course, the distance between any 2 points, the shortest distance is a line between those two. So we know this is going to be shorter than the sum of these two. So what we have to do, is we don't know this yet, we need to add these two up because she travels this way, then she travels this way, so we add those two. So 34 blocks plus 16 blocks gives us 50 blocks. So she travels 50 blocks on her bike. But we're going to have to find the straight line distance between her starting point and her ending point so we can compare and see how much shorter this was than going this way. So we need to find this distance or length, and then we'll end up subtracting it from the 50 so that we can figure out how many more blocks she has to travel going with her bike. So to do that, we use Pythagorean Theorem. So by Pythagorean Theorem, we start with a hypotenuse. I'm going to call this d for distance. So this would be d squared equals, and then one of the legs, 34 squared, plus the other leg squared, that would be 16 squared. Then from this point we start solving for d. We need to solve for d squared first. So d squared is, when you use the order of operations, we need to square before we can add. So when we square 34, we get 1,156, and then that's plus 16 squared is, of course, 256. So d squared is equal to the sum of these two. When you add those two, you'll see you get 1,412. Now, they didn't say anywhere in here, they didn't say specifically to approximate, but they did say about how many more blocks. So we're going to approximate here. To get rid of the square, we need to take the square root, but we need to do it on both sides to balance the equation. So the square root of d squared is d. And then when we take our calculator and you put in the square root of 1,412, you get about 37.576588846 and so forth. It's an irrational number, goes on forever. We're in a round. Didn't say anywhere in the problem what we need to round to. Consider the problem itself. She just wants to know about how much in blocks. That's not very precise, so we could probably get by with going and rounding to the nearest ones place or the nearest block. So I'm going to go ahead and round this to the nearest block or ones place. That's 38, about 38 blocks. So she would go a distance of about 38 blocks if she could go straight over to her mother's company, which obviously she can't because she has to go this way. So now we take this and we subtract it from the 50 blocks she has to go this route to see how much more she has to travel by doing this. So when we subtract those, and we get about 12 blocks. So she has to go about 12 blocks more on her bike than she would if she could just go straight to her mother's place of work. Example 6. One wall of a living room is 20 feet and the other wall is 11 feet. The owner of the house is planning to paint a mural on the wall and wants to figure out how long he needs to paint the decorative line from corner to another corner diagonally. How long should this line be? Rounded to the nearest tenth of a foot, and then it also wants it in inches, feet and inches. So let's go ahead and draw the wall of a living room. We're going to assume it's rectangular. Most walls are. So this will represent this man's living room wall. Okay, so this would be the bottom corner, you know, where there are chairs and the carpet's down here and then the ceiling's up here. And then it gives us the dimensions of the living room. So the length of it is 20 feet. And the height would would be 11 feet. Pretty tall roof there. Okay, so he's going to draw some sort of decorative line on one of the diagonals. Let's just say it's this one. So I'm going to take my straight edge, and just to be more accurate, I'm going to use a dashed line here. And this is how long, the length of this diagonal is what we need, so I'm going to call it D. Well, we assume, again, the living room is a rectangle, so this is a right angle. So therefore, this is a right triangle, and so again, by Pythagorean Theorem, we can use that theorem to set up an equation to solve for D. So we have the hypotenuse squared, or D squared, equals one of the legs, 11 squared, plus the other leg, 20 squared. And then solving for this, remember we're going to want to just figure out how long that is in feet, and then we want to do it in feet and inches. So this will be in feet because everything's in feet here. So this is D squared equals, remember we have to add before, we have to square before we can add in the order of operations. So 11 squared is 121, plus 20 squared is 400. Then we get D squared equals, adding these two together, let's say we get 521. Now, to solve for D, we need to get rid of the square on the D. So we use the inverse operation of taking the square root. So we do that on the left side, which means we have to do it on the right side. The square root and the square, quote-unquote, cancel each other out, and D is, let's see, approximately equal to, putting that in your calculator, and rounding to the tenths place here, we get about 22.8 feet. Okay, so that's how long that decorative line is going to be in just feet, about 22.8 feet. But we also want it in feet and inches. What I'm about to review with you is called dimensional analysis, where we use rates or ratios with equivalences so that we can find out other measurements. Hopefully you'll recognize this, but if you don't, take note of it. When we want inches out of this one measurement here, we have to use the fact that there are 12 inches in 1 foot. But we're going to use it as a ratio. And depending on how we're setting up our problem will depend on whether we put 12 feet or 12 inches on top or the bottom of the ratio. So what we do is we start with, we say the distance is 22 feet, and then we take whatever's left over, the 0.8 feet. We're going to add 0.8 feet. Then we're going to multiply that with a ratio using these two measurements. Now, where do we put feet and where do we put inches? That's determined by the units right up here. We're wanting inches, so that means we want to get rid of these feet right here. To get rid of these feet, if feet were down in the denominator of this fraction, they'll end up dividing out. If we put feet up here, they won't divide out. We'll get feet squared. So we want feet in the bottom and inches on the top. Plus, we want inches in the top so that we end up with inches. That's exactly what we're looking for. So put inches up here, feet down here. Inches, it's 12 inches for every 1 foot. So it's 12 inches to 1 foot. That's the ratio that we use, or the rate. Then at this point, we have 22 feet plus, and this would be 0.8. Once the feet divide out, and get rid of the ones because those are in the denominators, we have 0.8 times 12 inches. We still have inches. So now everything's set up for inches. So we have D is about 22 feet, and then when you multiply 0.8 times 12, you get 9.6 inches. So 22 feet, 9.6 inches is our answer in feet and inches. Example 7. A 20-foot ladder is placed against the side of a building with the bottom of the ladder 5 feet from the base of the building. If the base of the ladder is pulled back an additional 4 feet from the base of the building, how far down from the top of the original ladder location will the ladder be once it is moved? Round all answers to the nearest tenth of a foot. Okay, so what they're wanting to know is they've got this ladder leaning against the building, and we assume the building and ground are a right angle or perpendicular, so they create a right angle. We've got a 20-foot ladder, and which is 5 feet out from the base of the building. Someone comes along and they pull the ladder this way another 4 feet. So the bottom of the ladder now ends up somewhere right about there. Well, if that happens, then the ladder, the 20-foot ladder, is going to be pulled downward from this point right here to where, probably right about to there. So now the top of the ladder from the original ladder location is from here to here. So this right here is what we're looking for. I'm going to call that X. How far down did the ladder get pushed down since it was pulled out 4 feet? Some sort of sense tells you that it would be 4 feet down, but it's really not going to be. So what we have here are two right triangles, one in the first position and one in the second position. So the first requirement is that you be able to see those two right triangles. If you need to, go ahead and redraw those right triangles outside the original drawing, something like this. Here's the original one, where that's 20 feet, and this is 5 feet. There's the building, there's the right angle, and the ground. Once it's pulled out, the height of this triangle is not going to be as high now. This gets pulled out 4 more feet to about maybe there. Now the ladder is still 20 feet, no matter what. It was 20 feet, it stays 20 feet. And now this was 5 plus 4 more feet, which gives us 9 feet. So now the ladder's pulled out 9 feet away from the base of the building in the second triangle. Again, they want to know how far down did the ladder come from its original position. To do this, we've used two right triangles. We used the Pythagorean Theorem twice. Obviously, we need this height, which is this one right here. And then if we take the new height, which is this one right here, we can subtract the original height minus the new height, and that will give us what's left over. That's just segment addition. We end up subtracting this amount right here from the original height, and we get what's left over. To do that, we need to know both these heights. So I'm going to call the first height height 1, and the second triangle I'm going to call it height 2. So, by the Pythagorean Theorem, actually we're going to use it twice, aren't we? I'm going to make two columns. I'm going to make one of the first triangle and the second triangle. Now remember, this is the first position of the ladder. This is the second position of the ladder. Alright, so before it's pulled out, this is 5 feet. This is 20, and this is h1. So using Pythagorean Theorem, our hypotenuse is 20. So we have 20 squared equals one of the legs 5 feet squared plus height 1, or h1 squared. And then we'll solve for h1 here in just a moment. And then to set up our other triangle here, our second position of the ladder, we've got our heights 2, and we've got still 20 as our hypotenuse. So I'm going to start with 20 squared equals, now the distance out from the bottom of the building is now 4 more, or 9 feet. So we have 9 feet, or 9 squared, plus the new height, or h2 squared. Don't forget to square those. Now we solve each one of these equations for h1 and h2, and then we can use segment addition and subtract those amounts to get our answer. So over here in the first triangle, or the first position of the ladder, we have 400 when we square 20 equals 25 plus h1 squared. Subtracting 25 from both sides, we get 375 equals h1 squared. To get rid of the square on the h1, because we're wanting to know what h1 is, we take the square root of both sides. This gives us h1 is approximately equal to the square root of 375. Will give us, rounded to the nearest tenth of a foot. The tenths is the tenths place there, so that would be 19.4, about 19.4 feet. Hold on to that answer, come over here and solve the other equation for the second position of the ladder, or second triangle. This is 20 squared, which is 400 again. This time we have 9 squared, which is 81, plus h2 squared. Subtracting 81 from both sides, over on the left here we get 319 equals h2 squared. To get rid of the squared, we take the square root, so those kind of cancel each other out, and we get h2 is approximately equal to, when we take the square root of this other side, square root of 319 rounded to the nearest tenth gives us about 17.9 feet. Now all we need to do is find the difference between those two, and we'll have the length, or the length between the original position of the top of the ladder to the new position. So we take 19.4 feet. Now remember, this is approximate. Subtract 17.9 feet, and there has been, the ladder has gone down from its original position about, real close to 1.5 feet. Example 8. The lengths of 3 segments are given below. First, determine if these lengths can indeed form a triangle at all. If so, what type of triangle do they form? Well, so this has basically got 2 parts to it. We want to first determine whether these lengths can even create a triangle. To do that, we need to use something from right before we left for Christmas, the triangle inequality theorem. That theorem enabled us to take the sum of 2 lengths and compare it with the third length to see if 3 lengths could form a triangle. So we'll review that, and then once we get through with that, if it indeed forms a triangle, then we can go on and use the acute triangle corollary or the obtuse triangle corollary to determine what kind of triangle it is. Or we could end up using the Pythagorean Converse, depending on what kind of triangle it is. So starting from the beginning here, let's see if these actually form a triangle. So by triangle inequality theorem, we're going to take combinations of the sum of each 2 and compare it with the third one. Remember, the theorem says that the sum of 2 of the sides has to be greater than the third side. So there's our first one. And then another combination, 19 plus 30 has to be greater than 35. And our third combination, 35 plus 30, has to be greater than 19. So as we go through each one of these, even if just one doesn't work, then we cannot form a triangle. If all three work, we have a triangle. So 19 plus 35 is 44, and that is indeed greater than 30, so that one works. 19 plus 30 is 49, and 49 is indeed greater than 35, so that one works. And finally, the last one, 35 plus 30 is 65, which is greater than 19, and that one works. So therefore, this is a triangle. Now, since it's a triangle, so and we can't really tell what theorem yet, because depending on what happens tells us which theorem we used. So I'm going to write by blank triangle corollary. And if it ends up being the converse, we'll change this, but it's either going to be the acute triangle corollary, the obtuse triangle corollary, or if it's a right triangle, it's going to be the Pythagorean converse. So, but the way we do this is we take the three sides, and we take the longest of the three sides, which would be this one right here, 35, and we say, okay, the longest side squared, we want to compare it and see if it's greater than, less than, or equal to the sum of the squares of the other two sides. So 19 squared plus 30 squared. So this is where our symbol will go right here. Well, 35 squared, let's see, is 1,225. 19 squared is 361. 30 squared is 900. So that gives us 1,225. I'm going to leave this blank. 361 plus 900 is 1,261. Well, 1,225 is less than 1,261. Therefore, since the longest side squared is less than the sum of the squares of the other two sides, this is an acute triangle. Now we can fill this in. Acute triangle corollary. This is an acute triangle. Now, one important note. The reason why we have continued to use the would-be hypotenuse first in our Pythagorean theorem, since we started this lesson, notice we didn't use this. We used this. We used a symmetric property, turned it around. You probably noticed that. It's because it helps us when we use the acute triangle corollary or when we use the obtuse triangle corollary. If it's less, if whatever's over here is less than, it's acute. If whatever over here is greater than, it's obtuse. This is why we use the c squared first on each one.